Hello, everyone. Let's start our lecture. And before we start our lecture, let's go what happened in the previous lecture. So the main message in the previous lecture was that, of course, the array factor, and when I'm saying array factor in this case is for n element linear, that means they are on a line, uniform, that means the amplitudes are the same between the elements of the array, and the phase has a progressive phase shift of beta with respect to the previous element. So this is the constraint that we have. So under this constraint, and assuming that the phase center is at the center of the array, then this becomes our array factor, where psi is in fact is the collection of phases that we have due to distance, kd cos theta, and electric phase, which is beta. So this was what we discussed, and D was the separation between the element, which is assumed to be the same between elements, successive elements, because that's part of the definition of uniform antenna array. And then I also said this is a very brief equation, but when you look at it, you don't really see the actual concept here, which is the summation of different phases. So you may want to also have this in mind, that this is essentially equivalent to the summation that we had. And this summation was in fact uh, the collection of phases between the elements. So this is equivalent to that, but we often use that because that's a summation that can have many terms, and capital N is the number of elements. Then we mentioned one of the particular type of the array is broadside. And in broadside, if this is your array, let's say an array along the z-axis, you want the main beam to be perpendicular to the antenna. So theta equal 90 would be perpendicular if I take the array along the z-axis. To satisfy that, we said we need to have beta equal 0. So we don't want to have any phase change between the elements of the array. So we made this example that if we consider this as a 4-element array, we don't broadside means if this is z-axis, broadside means you want to have the main beam at theta equal 90. So you want this to be the main beam. So you see all of them are theta equal 90. So in fact, you are covering the azimuth plane. If you want that, you shouldn't have any phase difference between your elements here. So essentially, that brings me to beta equals 0. But then we mentioned that you may get into the situation that you satisfy this theta equal 90 by beta equals 0, but at the same time, you may have another main beam too, which is undesired. For example, a main beam in this direction. So you essentially have two main beams, one, let's say, toward you, one in this direction. And toward you is, of course, part of theta equal 90, so that's fine. But then let's say this one would be theta equal, let's say, 30 with respect to z-axis. So we don't want that. So we say, okay, what should we do to avoid these undesired main lobes? And we had a name for that. We called them grating lobes. So these are the undesired one. So we said we don't want grating lobes, and if you want to make sure that you don't have grating lobes, then we said the separation should be smaller than lambda. So essentially, if you want to have a broadside array, beta needs to be equal to 0, and d is smaller than lambda. And when we say broadside in this case, I haven't really made any assumption on the type of elements that I have here. So it's a broadside. I may call it maybe broadside array factor, because now elements are not here. So this is also something to keep in mind, that right now I'm just discussing the array factor. So when I'm saying broadside means array factor has a maximum at theta equal 90, because then you may use an element. For example, let's say if you use this dipole here as the type of your antenna, now you know that this dipole, if it's horizontal, is not going to radiate this way. So although you have a maximum in this direction, but when you find the total field of this array, the electric field of the single antenna element times array factor is going to cancel your maximum at theta equal 90. So you need to be careful that you create a maximum with your array factor, but then your single antenna element can cancel that. Remember that the total field was the single field times array factor. So you may get a maximum here, but then if you get a zero null with the single element, the total would be also zero. So just be careful about that. That our discussion is right now on the array factor. So I'm assuming that when you're using this, you're going to use an appropriate antenna element. So this is our broadside. Now, there is another special case which is called endfire. So, and that's essentially the discussion right now. So endfire essentially means if you have an array, let's say this is my array. If this is my array, you want the main beam to be along the axis of the array. So this is the axis of the array. So I want the main beam, let's say in this direction. Or maybe this is, I mean, this is also axis, of course. This is the main beam in this direction. So if I take this to be Z axis, I want my main beam to be either along theta equals 0 or theta equal 180. So downward. So either theta equals 0 or theta equal 180. So if I go again by assuming that the elements are on the Z axis, so like this. So this is my Z axis. Endfire essentially means main beam either at theta equals 0 or at theta equal 180. So this would be your maximum of the array factor, or this would be the maximum of the array factor. Of course, this is theta 180. This is theta equal 0. Now, the question is, how can we get something like that? How can we make sure that we can have something like this? And that's the question that we need to answer. So we're going to do the similar thing as we did in the previous case. So we say, okay, if we want to have maximum of array factor at theta equals 0. So let's find that. So for example, let's focus on this case. So remember, at what condition your array factor becomes maximum? Remember, the condition to have array factor maximum is that both numerator and denominator will go to 0. So essentially that requires that psi divided by 2 is n pi. If that happens, of course, that's going to become sine n pi. This becomes sine capital N times n pi. Both of them are 0. So that's one way to look at that. And if both of them goes to 0, you get a capital N based on the previous lecture. The other better way, in my opinion, to look at that is to look at this one, and you automatically realize that if psi divided by 2 is n pi, then psi is, of course, 2n pi. And if you substitute psi equal 2n pi here, all of these e to the power of j something becomes 1. So you're gonna sum 1 all the way to 1, and then you get capital N times 1, and then array factor becomes capital N. That means all of the elements are going to arrive in phase at theta equal 0. So this is the condition that we need to satisfy. So if psi divided by 2 is n pi, then I can write, of course, as you know, psi is 2n pi. So let's write psi. Psi is kd cos theta plus beta. I want it to be 2n pi. Let's choose the simplest one, which is 0. So let me choose n to be 0. So let's have that 0. And then my beta right now becomes minus kd cos theta. And I know that I want theta to be 0 for endfire. So minus kd cos 0. And that's going to be minus kd. So that means if my beta is minus kd, then I get a maximum along theta equal 0. This is the situation that I have. And this is different than broadside, of course, because remember, for broadside, beta was 0. Now here is beta is equal minus kd. Now let's check that together to see if that makes sense or not. So this is something that we should we could check potentially. So let's keep that in mind, and I'm going to make an example to try to check this. So let's make a simple example. Let's assume this is z-axis, and you get two elements here. And let's assume these two elements are separated by d equal lambda by 4. And now I'm assuming that this is I naught e to the power of minus j beta divided by 2. This is I naught e to the power of plus j beta divided by 2. I mean, the reason I did that, the way that I did that, is to ensure that I have my phase center at the center of the array. I could have just said I naught and I naught to the power of j beta, but I wanted to have phase of 0 here. So, I mean, this is essentially up to you. So if that's the case, this is my antenna array that I have right now. And based on this thing that I have, what is my beta? Beta is going to be minus kd. And k is 2 pi lambda, and d is lambda by 4, so it becomes minus pi divided by 2. So my beta becomes minus pi divided by 2. So let's substitute that here. So beta minus pi divided by 2 goes here. So this becomes pi divided by 2 by negative sign. So it becomes plus j pi divided by 4. And this becomes minus j pi divided by 4. Okay, so this is the situation that I have in terms of excitation. So that's my beta, which was minus kd. Now, let's see what's going to happen at theta equals 0. So let me observe what's going on along the z-axis. So this is me observing what's going on here. So I'm standing in the far field along the z-axis. This is my theta equals 0, and I'm just want to check if this is the maximum or not. How do you check it if this is the maximum? To be maximum, these two need to arrive in phase at the observation point. Now, how much this and the signal from this antenna needs to travel to get to here? So let's say it needs to travel for some distance. Let's call it distance. Let's call it, for example, maybe let's call it capital C. It needs to travel this much. How much this second antenna needs to travel? It's C plus lambda divided by 4, because this needs to travel more. So if it travels more, how much it travels more? By lambda by 4. So it's going to have a phase lag compared to this one because it needs to travel more. So how do you calculate phase lag? You would say, okay, phase lag that this is going to have is wave number. So maybe I can just write phase lag. It's going to be wave number, k. This is my k, wave number, times the extra distance, which is lambda by 4. And that's going to be pi divided by 2. So this is the phase lag that antenna number, let's call it number 2 and number 1. Antenna number 2 is going to have with respect to antenna number 1. But this phase lag is due to extra distance. But now, if you look at the excitation, this is the electric excitation, you see that this one, in fact, has a phase lead compared to this one. Remember, the more negative, based on our convention, is phase lag. So this is phase lag compared to this one. This is plus, this is minus. So the difference between these minus pi divided by 4 and pi divided by 4 is pi divided by 2. And because this one is positive with respect to this one is phase lead. So antenna number 2 now has a phase lead of, again, pi divided by 2. So you see, this one had a phase lag because of distance, extra distance. But then you compensated for the extra distance by this fantastic phase that we found here, because this is the trick here, to compensate for this distance. And it did compensate for this distance. And you see phase lead of pi divided by 2, phase lag of pi divided by 2, they cancel the effect of each other. So essentially, the radiation from these two arrive in phase here. And that's the beauty of this antenna array. So when I say beta is something, that essentially means beta needs to be equal to that to compensate for the phase lag or phase lead due to extra distance, so that I get a maximum, let's say in this case at theta equal 0. So this is the situation that I have. Now, let me again go to the same concept. Now, imagine again back to this antenna. This is your antenna, and now you design beta to be minus KD, and now you have a maximum radiation along theta equal 0. But now, how do you know that this is the only maximum? Because remember, psi was 2n pi, right? But then I chose just the simplest form of 2n pi, which is 0. But how do you know that this is, okay, this is your maximum, I agree, but how do you know you don't have a maximum at theta equal 90? That would be undesired maximum. And therefore, that's going to be your grating lobe. So you don't want your grating lobes. And therefore, we need to see how can we make sure that there is no grating lobes. So let's figure this out. So let me start by again discussing the same thing. So if you remember, to have maximum, we said psi 2 should be n pi, or equivalently psi should be 2n pi. So this is the situation that we have, and we said, okay, our KD cos theta plus beta should be equal to 2n pi. Now this time I'm not choosing the simplest one, I'm just choosing the 2n pi. But now I'm fixing my beta to the one that I found, which is minus KD. So now it's going to be KD cos theta minus KD is equal to n pi. So this is what I have. Now, so this is going to give me problem if there is a solution other than theta equals 0. So of course, for theta equals 0, everything is satisfied, because if theta is 0, cos of 0 is 1, KD minus KD is 0, and 0 can be equal to 2n pi when n is 0. So this is okay, but I want that to be the only solution. So to make sure that this is the only solution, let's try to find perhaps cos theta. So let's divide everything by KD. So cos theta minus 1 becomes 2n pi divided by KD. And instead of K, let's write 2 pi lambda and D. So 2 pi and 2 pi cancel. And then I'm going to get cos theta equal 1 plus n d divided by lambda. So this is the question that you need to be concerned with. So you should ask yourself, can I satisfy this equation? Of course, you can satisfy it for theta equals 0, because that's what we designed it to have maximum at theta equals 0. If theta is 0, this is 1, this is 1. So you can satisfy it by assuming n is equal 0. Now, if n is positive, let's say plus 1, plus 2, plus 3, you're not going to satisfy this equation, because then the value of cos becomes greater than 1. 1 plus something positive. So positive n is out of the picture. What about negative n? Let's say if n becomes negative 1. So if n becomes negative 1, you might actually be able to satisfy that. Let's say, for example, your n is negative 1. Let's make an example. Your n is negative 1, and then d divided by lambda becomes 2. If that happens, then this is becoming 1 plus n minus 1 divided by 2, and this becomes minus half. So that's going to have a solution. So cos theta becomes minus half, and therefore you can have a solution in this case, because it's between 1 and minus 1. So you essentially want to make sure that d divided by lambda is in a way that this is never satisfied. So to do that, d divided by lambda should be smaller than half. But let's go to the limit of that. If d divided by lambda becomes half, then what's going to happen? It becomes 1 plus minus 1 divided by half. It becomes 1 minus 2, which is minus 1. Minus 1, you still have a solution, because you know that theta equal 1 AT satisfy that. So if d divided by lambda become exactly half, you not only get a desired beam at theta equals 0, but on the other hand, you also satisfy theta equal 1 AT based on this. Although theta equal 1 AT is part of endfire definition, But if you want theta equal 180, you usually desire to only have theta 180, not both of them at the same time. So for this case, theta equals 0 is the main beam. This is the grating lobe if it happens. So you see, d divided by lambda get you at the limit. But if d divided by lambda becomes smaller than 1 divided by 2, let's make an example. Let's say 1 divided by 3. Then it becomes 1 minus 3. And then this becomes minus 2. And of course, cos theta cannot be equal to minus 2. So there is no solution. So then based on this, I can say to have no grating lobes. So if you don't want to have grating lobes for this example, then d divided by lambda should be smaller than half. And that means d needs to be smaller than half a wavelength. So the separation between the elements should be smaller than half a wavelength. For example, like this, that d is lambda divided by 4. That's okay. So this is d smaller than half a wavelength. So let's summarize our finding here. So we said if you want to have an endfire antenna, but endfire can have two forms, theta 0, theta 180. And this is for theta equals 0. Then beta needs to be minus kd, and d needs to be smaller than half a wavelength. Compare this to broadside, where d needed to be smaller than 1 wavelength. This is half a wavelength here. Okay, now, so let's consider one case before moving on to the next case, which is for theta equal 180. I want to discuss grating lobe here. So this example that I did here, I want to now make it in a way that you have grating lobe. So let's have a look at this example. But now this time, instead of lambda divided by 4, I'm going to choose something to not satisfy this. I'm going to make it lambda divided by 2, exactly lambda divided by 2. And then let's see what's going to happen. So let's change that to lambda divided by 2 this time. So you're going to have grating lobe. We just want to see that. So conceptually. So let me get rid of these. Okay, so if this is d divided by lambda divided by 2, then what would be the phases based on this? Because now I changed the distance, lambda divided by 2, beta will change. Beta becomes minus kd, it becomes minus 2 pi lambda, lambda by 2, that becomes minus pi. Beta becomes minus pi, therefore, let's go again by our initial thing, I naught e to the power of minus j beta divided by 2, I naught e to the power of plus j beta divided by 2. So the phase difference is beta, electric phase. Now, if beta is minus pi, this is going to be plus j pi. And this is going to be minus j. I should have said j pi divided by 2, of course, because this is beta divided by 2, and this becomes I naught e to the power of minus j pi divided by 2. So that becomes my new excitation based on that, and the difference between the distance in this case is c plus lambda divided by 2, because now the separation is lambda divided by 2. Now, again, I'm sitting in the far field looking at this antenna structure. Now, you see, this is the distance from this antenna to the observation point is capital C. The second one needs to travel more, C plus lambda divided by 2. So the second one has a phase lag with respect to first one because of the distance. And how much is this phase lag? To calculate phase lag, multiply wave number to the distance. So wave number is 2 pi lambda. The extra distance that this needs to travel to get to here is lambda divided by 2. So that's going to become pi. So this is the phase lag that it has. Now, let's look at the phase lead that this has, because look at this, the electric phase is now positive here, negative. So now antenna 2 has a phase lead with respect to antenna 1. So let's calculate its phase lead. So it's going to be pi divided by 2 here. This is minus pi divided by 2 here. So if you subtract them, you get pi. So this one has a phase lead of pi. So you see, phase lag was pi, phase lead was pi. So essentially, when they arrive here, they arrive at the same time. So you might think of it this way, that because this has electric phase, phase due to electric excitation as phase lead, is like, for example, it starts radiation earlier than this one. But this earlier radiation needs to travel more to get to this antenna. And by the time that it gets to this antenna is also radiated. So it compensates for the extra distance that you are traveling here. Now, this is not the whole story. I just showed that I get my maximum radiation at theta equals 0, but based on this criteria, you know that because you don't satisfy that, you get grating lobes. And previously, I told you your grating lobe would be at theta equal 180 in this case. So now I'm going to do it this way. Now I'm sitting at theta equal 180, and I'm looking at the radiation coming from this antenna, and I want to show it to you that here you're also going to have a maximum radiation. So how can you show that? Then you go to the antenna number 1. So this time, everything was, we were focused on antenna number 2. So all the lag and phase leads are for antenna number 2 with respect to 1. Now let's do it reverse. Now let's focus on antenna number 1. So now whatever I'm saying is for antenna number 1 with respect to number 2. Now antenna number 1 needs to travel extra. So d lambda divided by 2. Antenna number 1 needs to travel extra to get here compared to antenna number 2. And because of this extra traveling, it's going to get a phase lag. So what is the phase lag? It's going to be 2 pi lambda times the extra distance, which is lambda divided by 2, and it's going to be pi. So that's the phase lag of antenna 1 with respect to antenna 2. Now, what about electric excitation? Again, you see, this is more negative compared to this one. So I'm going to say, okay, this also has a phase lag with respect to electric excitation. So let's like its phase lag, because this is more negative compared to this one. So at this point, you may become confused that this is phase lag, this is phase lag. So how come they get in phase at theta equal 180? Let's check that. So what is the phase lag? Minus 90 to plus 90, 180 difference. So the phase lag is 180, and 180 is pi. So you see, antenna number 1, when it's radiating downward to theta equal 180, has a phase lag of 180 due to extra distance, has a phase lag of 180 due to electric excitation. So in total, it has 2 pi phase lag. So 2 pi phase lag essentially means no phase difference. So that the only thing that it means is that if this is the antenna number 1, right? Let's say if this is the antenna number 1, so phase lag of 2 pi means essentially you're losing 1 cycle and you start from here. So, but as you see, they're going to be on top of each other. They're going to be in phase. So 2 pi phase difference is essentially saying that there is no phase difference. 0 phase difference, 2 pi phase difference, 4 pi phase difference, 6 pi phase difference, they're all the same thing for us. So that's why this is going to have a maximum at theta equals 0 and theta equal 180 at the same time. So, and therefore it has a grating lobe. So I just showed that if you don't satisfy that, you get another maximum 2. And if you make it even worse, let's say d equal lambda divided by 4, you may start having more grating lobes. So this is essentially what I wanted to mention here. Now, the other thing I wanted to mention here would be the other type of end fire. So end fire with the main beam at theta equal 180. So how do you find that? So again, you go by the same logic that psi 2 should be n pi, therefore psi should be 2 n pi. So you're going to substitute for psi kd cos theta plus beta, and you go with the simplest one, which is 0. Therefore, and you know that cos theta in this case should be cos 180. Cos of 180 is -1, so this becomes minus kd plus beta is 0. Therefore, beta is plus kd. So, end fire at theta equals 0 was beta minus kd. Now I'm going to write end fire at theta equal 180 should be beta equal plus kd. So this is minus kd and plus kd. And now with this one, you also want to make sure that theta equal 180 is the only main. We don't want to, for example, have another one, let's say at theta equals 0. So you essentially need something like that. And if you go through the derivation of this one, you see that this also follows the same thing. So for this, you have the same rule. D should be smaller than half a wavelength. So that's for the other type of end fire. Now, to summarize the discussion in this part, let me write broadside here too. This was maximum at theta equal 90, and beta in this case should be 0, and D is smaller than wavelengths. Something I want to mention again here, I've already mentioned that several times, but just to be clear, remember theta equals 0 is this angle. So this is the main beam theta equals 0, assuming that the axis of the array is Z. This is theta 0. This is theta 180, but theta equal 90 means 90 or 90 or 90 or 90. So the whole plane here is theta equal 90. So when you say, I want to have a main beam at theta equal 90, that means your main beam covers the whole azimuth plane. So the whole, this plane that's cutting this antenna, that's theta equal 90. This is the XY plane. So essentially, if I'm the antenna like that, so if this is my main beam covering the whole plane like that, this is broadside, theta equal 90. Whereas for end fire, you essentially looking up, theta equal 0, or looking down, theta equal 180 here. Now, for the next discussion, we're going to take a look into phased array antenna, which you can have, for example, arbitrary theta. Let's say theta equal 30 main beam. Okay, let's start our discussion on the phased array. So you see, these were specific cases, theta equals 0, theta equal 90, theta equal 180. Now, what if you don't want any of them? What if you want theta equal 30, for example? So then how do you find this beta? So it's going to be exactly the same procedure. I'm going to show it to you, but let's first start with an angle, let's say theta naught. So let me remove this and see how can we figure out those angles. Okay, just while I'm writing, I want you to think about, for example, an angle, let's say theta equals 30, and imagine that angle in the spherical coordinate. I'm going to get back to that later with you. So here, that's going to be, we're going to talk about phased or a scanning array. So in this case, you essentially want to have theta max, the maximum radiation, to be theta naught. So you know that we considered three particular cases of theta naught, which was theta equals 0, 180, and 90. So these were the special cases. But what if theta equals 30, for example? So now what should we do? So let's do it the same way. We said to have the maximum radiation, psi divided by 2 should be n pi, or psi should be 2n pi. Psi was kd cos theta, that's the phase due to distance, and beta is the electric phase that we have, and we chose the simplest one, which is 0. And of course, now you say, okay, I want my maximum to be theta 0, so I want to satisfy that for the maximum. So you say kd cos theta 0 plus beta needs to be 0. Therefore, beta should be minus kd cos theta naught. So this is what we have in general. And this is consistent with broadside, because if it's broadside, then you have cos of 90, which is 0, beta becomes 0. If this is theta equals 0, you get minus kd. If this is theta 180, you get plus kd. So everything makes sense in this case. So this would be the phase that you need to make sure that you get your maximum at a certain angle, let's say theta 0. So let's verify that together. Maybe we start with an example. And for example, our example could be, we have, let's say, a separation. Let's make an example that makes it easy. Lambda divided by, maybe lambda divided by, let's say lambda divided by 2. And then let's assume that we want a theta naught to be 60 degree. And let's check if that's going to satisfy that or not. So we are essentially saying that the separation is lambda divided by 2. Let's go 2 elements to have it easy. And theta naught is 60 degree. So based on this, my beta becomes what? Beta becomes minus k. K is 2 pi lambda. D separation is lambda divided by 2. Cos of 60 is half. So I'm going to have lambda, lambda cancel. 2 and 2 cancel. I get minus pi divided by 2. So this is beta that I have between the two antennas. So let's have two antenna here. And so I need to plot it a little bit better. So this is like that, so that this distance and this distance are the same. So I know that this one is I naught e to the power of minus j beta divided by 2. This is I naught e to the power of plus j beta divided by 2. So minus beta divided by 2 here, plus beta divided by 2 here. The phase difference is beta. And I know that for this specific choice, beta is minus pi divided by 2. So let's substitute beta minus pi divided by 2 here. So this becomes plus j pi divided by 4, and this becomes minus j pi divided by 4. So this is what I have. And I know that the separation is lambda divided by 2, so this is lambda divided by 4, and this is lambda divided by 4, so that in total they become half a wavelength. Now let's check theta equals 60. And to make sure that with this beta, I get actually a maximum at theta equals 60. Let's check that conceptually. So this is now 60. So this is my 60 degrees. And now in the far, you are sitting in the far and looking. And you want to check what would be the signal that you're getting from the antennas. Now, if you are in the far, the first antenna, the distance that it needs to travel to get to you is R1. And of course, R1, let's call this first antenna, and this is the second antenna. The second antenna needs to travel R2 to get to you. So what is R1, what is R2? We need to know the difference between them. So let's call this R from origin to there R. Therefore, R1, based on our phased approximation, is R minus the projection of this on here. So I'm going to project this here. So minus this. And this is lambda divided by 4 cos 60. And then what about R2? R2 is R, but this time plus this much. And this much is again the same thing, lambda divided by 4. This angle is also 60, so it becomes plus lambda by 4 cos 60. So R2 minus R1, the difference between R2 and R1 becomes 2 lambda 4 cos 60, and cos 60 is half, 2 and half cancel, it becomes lambda by 4. So this is the difference that this, the extra difference that this needs to travel to get to there. Now, because of this extra travel, antenna number 2 is going to have a phase lag of k, which is 2 pi lambda, times the extra distance. And extra distance is lambda divided by 4, and that's going to be pi divided by 2. So this is going to have a phase lag with respect to this one by pi divided by 2. But now look at the electric excitation. This is the phase lag due to a space, due to distance. But this one has a phase lead because of the excitation, because your beta was negative, remember? So when we plugged it here, it became positive. Now, how much of phase lead this one has compared to this one? It has 90 degrees. So I'm going to have the phase lead of pi divided by 4, and minus pi divided by 4, it becomes pi divided by 2. It becomes 90 degrees. So it has a phase lag of 90 degree, it has a phase lead of 90 degree, and therefore based on this, we're gonna cancel these two. So when they arrive at this point, they become essentially in phase. So phase lag and then phase lead, and that's the situation that we have. So the phase lag and phase lead cancel the effect of each other, and you get your maximum at theta equals 60. Now, something to keep in mind about this theta equals 60 in a spherical coordinate. You see, if this is the z-axis, what is theta equals 60? So this is z-axis, theta 10, 20, so on. And now this is theta equals 60. But remember, this is not the only theta equals 60. This is in fact theta equals 60. So it can rotate. So when you say I have a beam at theta equals 60, that means your beam is like a cone that goes around the antenna, and this angle is theta equals 60. So this is the cone that it covers the area around the antenna. So theta equals 60 is not single angle like that. It's just everywhere around. And when you think of theta equal 90, that's also a cone, but this is the cone that we know, but theta equal 90 is like a flat cone. So when I say if I'm the antenna, theta equal 90 is the azimuth plane. It's a flat cone. But if I'm saying theta equal 30, perhaps I'm the z-axis, my hand would be theta equal 30, but it can go around. So the whole thing would be theta equal 30. So you're covering it like that. But then theta equal 0 is one angle, theta equal 180 is only one direction, I should say. Okay, so this is that, and now I would say let's go and look at some slides together from the textbook. Thank you.